We are your way again. We are now going to consider the physical properties of covalent substances, having looked at all the other terminologies and concepts associated with covalent bonding. Now we are able to understand certain physical things that we have observed in nature. Covalent bonding or bonding is going to explain all of them. We have looked at dative covalent bonding, we have looked at polar and nonpolar covalent substances, we have looked at molecular covalent substances, and we have looked at giant covalent substances. They behave in certain ways in nature. And now that we have studied the chemistry behind all of them, we are able to explain why they behave in such a manner. So physical properties. The physical properties are the physical things that we see with our naked eye in our everyday life. So that is the fifth point. So I will say my E of covalent bonding, physical properties of covalent compounds. Now the first one, I'll start with giant covalent substances. Giant covalent substances. Remember, giant covalent substances doesn't mean it is polar or nonpolar. But when I was describing polar and nonpolar substances, I need to tell you now that giant covalent substances, most of them are nonpolar. Almost all of them are nonpolar. Now, giant covalent substances, what do you think will be the first physical properties? Looking at diamond, I have said it several times in most of our videos. What did I say? I said diamond is a very hard substance. Silica is a very hard substance. That is what is used in doing the POP in our ceilings in our rooms or houses. It is used as POP when someone is injured in the hospitals. That is silica. And the plastic is very hard. Sometimes plastic is quite hard, and so on. So giant covalent substances, the first physical property is that they are hard, or they are harder than the simple or covalent molecular substances. Let's see an example. This is plastic. If I try to break it, it's very difficult to break. Okay, I'll have to force it before it breaks. That plastic, if I want to break it, it will be very difficult before it breaks. Now let me take any simple substance. Like here, we have sugar here. It's also quite light, but it is still, sugar is quite light, but it's still a molecular covalent substance. This is sugar. I have some molecule here. You see, even as I'm trying to pick it, it is breaking away. The particles are breaking away. So I can easily, just with laser force, I've smashed it into particles. It's broken. Why? Because the intermolecular forces in the sugar molecule, which is covalent molecular compound, is what? Weak. This sugar, the forces there, the intermolecular forces there are van der Waals forces, which is very weak. Whether it is dipole or it is even induced dipole, it is quite weak. So the sugar is soft. That is why sugar, even if it is cubes, you can easily do this and to break. And so mostly sugar comes in very tiny particles. You have seen that. That is a large molecule, but it's still a covalent, simple covalent molecule, and therefore it is weak. It is not as hard as any of the four identified giant covalent substances. Now, because of this same reason, number two, giant covalent substances have high boiling points and melting points. They have what? High boiling point and melting point. It is hard. The intermolecular forces are high. So if you want to boil it, you need to heat it up to a certain degree before you can break the intermolecular forces for it to begin to evaporate into the air. So giant covalent substances have high melting point and boiling point due to the strong intermolecular covalent bond that exists between them. Now, number three, the giant covalent substances mostly are insoluble in polar solvent. They are insoluble in polar solvent because why? They are nonpolar. Neither do they have hydrogen bonds. You cannot dissolve diamond in water for it to dissolve. Never. It will not dissolve. You cannot dissolve graphite. This is my graphite. I cannot dissolve it in water for it to dissolve. It will remain in there forever. I cannot dissolve this plastic in water. You know it. It will remain in there forever. So they are insoluble in polar solvent because they are polar. They are nonpolar. So if they are nonpolar, what happens? It means that if you drop them in the polar solvent, there is not going to be any interaction between the giant covalent substance molecule and the water molecule. So there is no hydration energy, or for that matter, solvation energy generated for it to overcome the intermolecular forces of the giant covalent substance. So no dissolution will occur. Number 4, for giant covalent substances, almost all of them do not conduct electricity, with the exception of graphite. All of them do not conduct electricity. Diamond does not conduct electricity because there are no free atoms, there are no free electrons or ions in there. Plastic doesn't conduct electricity. I have some electrical conductivity system here. You see, I have my bulb, I have my batteries connected. If I add this wire to this wire, what do you see? I have the light here. Now, let me intersperse them in between with plastic. This is plastic. I put another plastic here. You see, it doesn't conduct electricity. It doesn't conduct electricity. However, assuming I got any metal and connected them, it will. Or let me even use water, not distilled water. Let me use polarized water. If I use this polarized water, you see that the light has come on. Let me remove it. If I put it there, you see the light on. Are you seeing it? Why? Because this water is polar, but it has ions. I have not come to molecular covalent substance in it, but I'm just illustrating it with as an example that once I have electricity flowing here, when I join the metals together, assuming I have a giant covalent substance, this plastic, and I join them, if it were to conduct electricity, the light should come on. But the plastic, which is a giant covalent substance, doesn't conduct electricity. That is the point number 4. Let me take my silica. I have my silica here. Let me dip them into it. Silica, any light on, no light. It doesn't conduct electricity. It doesn't conduct electricity. So that is it. I don't have diamond here, so I cannot illustrate it done. But what about graphite? I said with the exception of graphite. What about graphite? I have graphite here. Let me see. Graphite is the one, that's black thing in the pencil. I have it here. Let me see if it will. Science is interesting. It doesn't lie. Look at graphite. I'm joining it. Do you see the light there? Interesting. The pencil, that black thing in your pencil. If you need a wire to do something you're not getting it, just break loose a pencil and tie it to the ends. It will give you the electricity. But of course, the degree of conduction below, because graphite, we'll explain later when we are treating graphite as a topic, for you to know why graphite conducts electricity. It has some free mobile electrons held in its structure. That is why it is conducting the electricity. But the electrons are few, and the mobility is also small. That is why they conduct electricity, but not as high. You see, when I take away the graphite with the metal, wire to wire, you see how the conduction is very high. But with graphite, it's quite low, because the electrons are not that high, and they don't move as high as we have in metals. So that is the difference. So with the exception of graphite, the giant covalent substances all do not conduct electricity, but graphite does. Point number 5 for giant covalent substances, they are generally solids in nature. Why are they solids? Because of the giant interlocking network of covalent bonds. Because of the giant interlocking network of covalent bonds. Let me summarize all the things that I've said under giant covalent substances. 1, for the strong intra and intermolecular forces, they are very hard compared to the molecular covalent substances. Diamond and another friend of diamond are now known to be the hardest substance on Earth. Graphite is hard, plastic is hard, silica very hard. Look at our POP in your room when you go home, and look at the POP that is used on fractured bodies. Very, very hard. Number 2, because they are hard, they have high melting points and they have high boiling points. Anyway, here I didn't even add, they also have high densities. They also have high density. All the physical properties, they have high melting point, they have high boiling point, they have high density, high enthalpy of vaporization or whatever, because they are all physical properties that you can measure. And they all be high because they are very, very hard. And that is due to the intermolecular forces and intramolecular forces between them. Number 3, they are insoluble in polar solvents. Why? Because they are all nonpolar. They are nonpolar, so none of them dissolve in polar solvents like water. 4, they do not conduct electricity with the exception of graphite. because they don't have any electrons or ions moving in them besides they are nonpolar. So if they are nonpolar, then they cannot conduct electricity. No ions, no polarity, and so no conduction of electricity. Number 5, they are generally solids in nature. At room temperature, wherever you find them, they are solids. Why? The same reason. Strong interlocking network of covalent bonds. That is why they are solids at room temperature. Now, let's go to molecular covalent substances. For molecular covalent substances, we have to identify whether the substance is polar or nonpolar. Okay? So, I'll be mentioning the physical properties. I'll mention the physical properties in relation to nonpolar and polar substances. 1. Almost all of them, here it is whether nonpolar or polar. Almost all of them, or most of them, let me put it that way, are volatile and so exist as gaseous substances. Particularly all those with van der Waals intermolecular forces. All those with what? Van der Waals intermolecular forces exist as gases and they are volatile. They exist as gases at room temperature and they are volatile. Volatile means that they easily evaporate or turn into air. Even those that are liquids are very, very volatile. A typical example is petrol. Petrol, when you go and buy it, and it's even a gallon, they tell you, cork it, close it. If you don't close it, by the time you go and come back the next day, everything is gone. Why? Because the intermolecular forces are still van der Waals forces. But because petrol is a molecule that is large in size, van der Waals forces increases with increasing size. So they don't exist as gases. Petrol is in nature exists as liquid at room temperature, but highly volatile. So if you just put your hand in it and spread it on your skin, 1 minute, everything is gone. They would have evaporated into thin air because the intermolecular forces between them will break. That is because they are weak. So for molecular covalent substances, all those with van der Waals forces they are either gases or we say they are volatile. Those that are large in size are those that are able to exist in the form of liquids at room temperature. Else almost all of them are gases. But those molecules, whether small or large, that exhibit hydrogen bonding or exist as liquids, because hydrogen bonding is a stronger intermolecular force than the van der Waals forces. Examples are the water or ROH, that is the alkanols, the acids, the ammonia, and then hydrogen fluoride exists as liquids at room temperature. Number 2, for molecular covalent substances, if you have a molecular covalent substance that is nonpolar, then it is insoluble in water. It is nonpolar. It is insoluble in water. Why? Because water is polar. And so if you put the nonpolar substance in the polar solvent, they will not interact in any way. They don't have any relationship. So there wouldn't be any hydration energy or solvation energy. In what? In water. But the polar ones are soluble in water because water itself is also a polar substance. So when you put them together, they will interact through what we call dipole-dipole interaction. A large hydration energy will be released and to break the intermolecular forces of the solid that you have put in the water, and that substance will dissolve in the water. Example, let's look at this oil. Remember, if I take this oil and I pour a little in, this water, that's my oil. Oil is an nonpolar substance. If I put it here, there will definitely be separation. No matter how hard you shake it, the water will be separated. The oil will be separated. It can never mix with it. It can never mix with it. Maybe I should have used. Oh, this is distilled water. Well, you can try it at home. You know it. This is not very transparent, but let me add some more and see. I don't want to waste all my oil. No matter how hard I shake it, of course, I think I'm praying that the video will be able to pick it. There'll be a separation between the oil and the water. The oil is on top and the water is down there. It will never mix. But if I add some like HCl, add HCl here. Yes, HCl. HCl is a polar molecule. Let me take this. HCl. HCl, that is hydrogen chloride, which is a polar molecule. Let me add water to it and see whether it will mix. That is it, sitting there. There is no separation. Totally mixed. Such that if you want to separate them, you have to use distillation process. Because they have different boiling points, you can use distillation to separate them. You boil, when HCl gets to its boiling point, it will move into the gaseous state and then come out, and you can condense it and you get your HCl. And then later, the water can also, or the water remain in the pot, okay, in the boiling pot. So HCl is a polar molecule. It mixes with water because water is also a polar molecule. So this one, for molecular covalent substances, solubility is based on whether you are polar or not. If you are polar, you dissolve in polar solvent like water. If you are non-polar, you can only dissolve in non-polar solvents. Okay. 3. The non-polar substances have lower melting point and boiling point than the polar ones. I think I've explained that already. Why? It is non-polar. So the force that will exist between it will be induced dipole. And that is very weak intermolecular force. The weaker the intermolecular force, the lower the melting and boiling point. And of course, also the lower the enthalpy of vaporization, the lower the density. So non-polar covalent substances have low melting point, low boiling point. They have low enthalpy of vaporization, and they have low densities because of the weak intermolecular van der Waals forces that exist between them. What is this van der Waals force? It's induced dipole. But if it is a polar molecule, then it is not induced dipole. That is dipole-dipole interaction. Dipole-dipole interaction is a stronger force than induced dipole. And again, if it is polar and the molecule is slightly large, it could even exist as a liquid. Because 1, the molecular force is dipole-dipole, which is strong. And then 2, it's a large molecule, and so it will add on to the strength. And conduct electricity because they don't contain any ions. Non-polar molecules do not conduct electricity because if it is a non-polar molecule, remember we said the induced dipole is even assumed, it is induced before that polarity can exist. So if it is a non-polar molecule, then we don't have any ions existing in that particular substance, and therefore it cannot conduct electricity. It cannot conduct electricity. Let me demonstrate it. This is my oil, non-polar covalent molecule. I have water here. Polar molecules will conduct electricity, but even that, they must be dissolved in solvent to make the ions move around before they can conduct electricity. So for instance, if I take my oil, this is my light, that is electricity, we can see it. Let me put it in the oil. Yes, the oil doesn't conduct electricity. We cannot see the light. Why? Because this oil I'm dipping the wire into is not polar. It's not polar. Let me take distilled water. This is pure distilled water. Distilled water means that it is pure, but there are no ions in it. So I'll try it and see. But first, before I do that, let me put this in. This is ordinary water, which has ions in them. Oh. Have you seen the light? I'll remove it. Let's see it again. It comes on. I hope you can see it in the video. Yes, so it comes on, and then when I remove it, it goes off. This tells you that the water here has some ions in it, but the ions are too low. Because remember, water is not purely ionic. It is polar, and therefore it can conduct electricity because it has some ions in it. Let me try the distilled water. The distilled water is pure water that is not supposed to have ions in it. So let's see whether we get a light. No light. In sugar too, sugar as a stand, though polar, the polarity is very small. But then if you dissolve it in water, they will stand on its own. It doesn't create any polarity in the water, and therefore sugar solution also doesn't conduct electricity. Let's see it. This is distilled water. So let me dissolve some sugar in it and see. You see, no light. No light. Science is wonderful. Okay? Of course, we try to understand nature. That is what one scientist said. He said, all I strive to do is to understand nature. When someone says like this, someone makes a statement like this and he's a scientist, of course, the reverend ministers and other things will be fighting him. Where they say you cannot understand God. You don't strive to understand God. But he knows why he makes that statement. I strive to understand nature, so that they can turn around what God has created for us to understand and make life easier for us. Without science, what do you think we will be doing by now? We would have been living in the old age. Now look at what happens. Drones and all that, taking pictures, and it is because people are constantly trying to understand nature. We scientists, we are not saying we are challenging God. Please, we want to understand what he created on earth so that we make the best use of it to our benefit. So that is what we do. Science is very interesting. So all these things that we have described are things that are real, and we try to ascribe reasons to them. So in general, the molecular covalent substances, I'm summing up. Molecular covalent substances are volatile, and most of them exist as gases at room temperature because they have weak van der Waals forces. Those that are large enough and have dipole-dipole interaction may exist as liquids, like petrol, because petrol, the compound is C7, so it's a bit large. The larger the substance, the higher the van der Waals forces, and then the stronger the intermolecular forces. So some of them approach the liquid state. Else, almost all of them are gases at room temperature, and they are very volatile because of the weak van der Waals forces. The polar ones may also have dipole-dipole interaction, which is stronger, and so some of them can exist as liquids as well. And these ones conduct electricity if they are mixed with solvents where the polarity is enhanced or where ions are generated in the system. They conduct electricity. Now again, the third one, we say that the polar solvents, the polar substances are soluble in water because they are able to interact with water through dipole-dipole interaction. And those with hydrogen bondings even dissolve them more because they will interact with water through hydrogen bonding. And those with hydrogen bonding, of course, have higher melting point, boiling point, enthalpy of vaporization than those with dipole-dipole interaction. And those with dipole-dipole interaction also have these characteristics more than the non-polar covalent substances. So these are the physical properties of of molecular covalent substances. I guess I have explained almost all the physical properties of these substances. In your type of questions, they will ask you to list, or they'll give you a molecule and ask you to give 2 or 3 physical properties of that molecule. You have to be able to identify that type of molecule, whether it is a non-polar covalent molecule, whether it is a giant covalent molecule, or it is a polar covalent molecule, and be able to mention any of these physical properties associated with it. What we have seen in your video and what we have summarized for you are general, but in questions, the question may be specific to a molecule. So you identify the molecule first and assign the physical properties that we have explained to each of them. We are not done with covalent bonding yet. We are not done with covalent bonding yet. We are still going to go on, and then we'll look at the intermolecular forces. But before we look at the intermolecular forces, we are going to look at what we call continuity of bond types. Continuity of bond types. And after that, we'll look at intermolecular forces as the last part of the topic, covalent bonding. Don't stay away. We are left with about 3, 4 or more videos to complete covalent bonding before we go on to the next major topic, hybridization. That is a further explanation of the nature and structure of all the compounds, of all the covalent compounds that we have seen or that we can see in nature. Thank you so much for being with us. Learn right, still in the business. We want to make you happy. Continue watching our videos and all your challenges will be solved. Even that, if you watch the video and you have our addresses where you have challenges, you want us to help you, just place a call and your answer will readily be given to you. Thank you so much.